Swayam Prabha. Digital India. Educated India.
Welcome to this next lecture on vibrations of plates and shells. So before jumping straight into the derivation of the Hamilton's law for a general shell, I was trying to give you the inconsistency on the whole theory through an example of the Euler Bernoulli beam. Okay, Euler Bernoulli beam. Now what I want to do is first I would like to derive the Euler Bernoulli beam equation, using Hamilton's law. Okay, in the most common way. I will do it in the most common way first. Okay, so that is what the Hamilton's law states, that this variation, okay, this variation of an integral between two time points, okay, of the difference between the kinetic energy and the potential energy is 0. Okay, and the states at the endpoints are known. Okay, for a dynamical system that is moving in time between two time points where the states are known, it behaves in such a manner that the variation of this action integral is 0. That is the Hamilton's law. Okay, so now let us form this U term here. Okay, that U term consists of one, the strain energy, and the other the from the external load. Okay, so the strain energy term is 1/2 the volume integral of sigma ij epsilon ij dV. Okay, and for our case of the Euler Bernoulli beam theory, only sigma x and epsilon x survive, every other term is 0. So what we have here is equal to 1/2, okay, the integral along the y direction, the integral along the x direction, which is 0 to L, the integral along the h direction, which is minus h by 2 to h by 2, sigma xx epsilon xx, okay, dz dx dy. Now there is no dependence in the y direction, so this will give me the width of the beam. Let us say it is b. Okay, so this becomes equal to or let's say let's hold on, let's hold on. Let us talk of the displacement u of x, which is now minus z dw by dx. Okay, then epsilon xx is equal to minus z d2w dx square. Then sigma xx is equal to E epsilon xx, which will be equal to minus Ez d2w dx square. Okay, and so my strain energy term I will write it as equal to b by 2 integral 0 to L integral minus h by 2 to h by 2, okay, E z square d2w by dx square whole squared dz dx. Okay, now only this z is a function of z, these are not functions of z, and so this ends up looking like b by 2 E h cube by 12 integral 0 to L del 2 or hold on d2w dx square whole square dx. Okay, and the u now, okay, the u now, which includes the load, external load, is given by E b h cube by 212 integral 0 to L d2w dx square whole square dx minus integral 0 to L the uniformly distributed load, the displacement under the load dx. Okay, this is per unit length. Okay, so that is the potential energy term. Then we have the kinetic energy term. Okay, so which is simply 1/2 mv square, that's integral 0 to L, okay, rho b h dx w dot squared. Okay, w dot squared. So then the Hamilton's law is delta variation from T1 to T2, the kinetic energy minus the potential energy dt, okay, or let me keep it as T, okay, let me keep it as T minus u, okay, so which can be now written as the variation T1 to T2 integral 0 to L 1/2 rho B H W dot squared minus E B H cube by 12 d2 W by dx square whole squared plus Q of x W of x dx dt. Okay. Now here now if we take the variation of this inside, it's a linear operator. If I take the variation, what happens? I have T1 to T2 integral 0 to L, okay, 1/2 rho B H W twice W dot delta W dot minus E B H cube by 12 twice W double dash delta W double dash, where dash is ddx, okay, ddx is a dash, plus Q delta W dx dt. Now as is standardly done, we will start transferring derivatives from the variational to the original term, okay. So what do we get here? This term we integrate with time, so I get 0 to L 1/2 rho B H twice W dot delta W T1 to T2, okay, minus, okay, integral T1 to T2 integral 0 to L 1/2 rho B H twice W double dot delta W dx dt. So we have done use a product rule here in integrating. So this is the first term, this is the second term. You can see that this derivative has been transferred to W dot, okay. Now the other terms. Other terms are this term and that term. So with the second term, what do? We have already a minus, so a minus integral T1 to T2. This we integrate with respect to L, okay. So I get E B H cube by (12), okay, then W double dash delta W dash 0 to L, and because this has a minus, the other term has a plus, integral T1 to T2 integral 0 to L E B H cube by 12 W triple dash delta W dash, dx dt. Okay, so one other thing I have to do, this will come in here, this will come in here, this will come in here. Okay, so this half will come in here, it will come in here. Okay, it's not related to this, that's why. Okay, so then the last term is plus integral t1 to t2 integral 0 to L q delta w dx dt. Okay, so now here we have a boundary term in time at the two endpoints, and we started the loss by saying that variation of w at the, w is known at the two endpoints, and therefore variation is 0. So this term is 0, this term we set to 0. Okay, so now what do we have? We have here minus integral t1 to t2 integral 0 to L 1/2 rho bh twice w double dot delta w dx dt, okay, minus integral t1 to t2 ebh cube by 12 w double dash delta w dash 0 through L, and this integral, again we are going to do a product rule here. So I get integral t1 to t2 ebh cube by 12 w triple dash delta w 0 through L minus an integral t1 to t2 0 through L ebh cube by 12 w fourth power derivative delta w dx dt, okay, plus integral t1 to t2 0 through L q delta w dx dt. So if we now, this is a boundary term, this is a boundary term, and this is also a boundary term. So if we collect the integral terms first, okay, so what do I get? I get integral t1 to t2 integral 0 to L okay delta w dx dt. I get minus rho b h w double dot, okay, minus e b h cube by 12 w fourth derivative plus q, and the two boundary terms, which is minus integral t1 to t2 e b h cube by 12 w double dash delta w dash 0 through L plus integral T1 to T2 E B H cube by 12 W triple dash delta W 0 through L. That should be equal to 0. I did not put that, okay. So, that should be equal to 0. It should be equal to 0, this should be equal to 0, this should be equal to 0, okay. And now for any arbitrary variation that is possible, this term must be 0, and so we set the differential equation and the boundary conditions to zeros independently. So, we have, for right from here, I am going to write it just here, E B H cube by 12 del 4 W by del X 4 plus rho B H W double dot is equal to Q. That is my Euler Bernoulli beam theory, beam equation, okay. And then of course I get my boundary terms. I am not dwelling so much right now on the boundary terms, we will come to it later, okay. But we have derived the Euler Bernoulli beam equation. One other thing is that in accounting for the kinetic energy, we have ignored rotational inertia. Okay. So, we will do that in our full plate and shell pursuit also, we will ignore the rotational inertia. That is why I am showing you this beam theory. Okay. Now, the way it is actually going to be done in the book, okay, actually the way it is going to be done in the book is this. The Euler Bernoulli beam theory, let me just state, it states that the plane sections remain plane. Okay. That means a section that was like this plane after deformation, okay, after deformation remains plane, remains plane. Means plane, okay. It means in an exaggerated sense it does not do like this, okay, does not do like that. The other is that normals to vertical planes remain normal, or let me say normals to cross sections, normals to cross sections. Remain normal to cross sections after deformation. Okay. So, if we have, I will make it thick. So, this is a cross section and there is a normal, okay. First of all, the cross section as it deforms, the plane section is going to remain plane. Plane section will remain plane, and this normal will be normal to this. So this angle is 90 degrees. This angle will also be 90 degrees after deformation. Okay. So these two together, what they do is they set epsilon xz to 0. They set epsilon xz to 0. Okay. There is a Timoshenko theory. There is a Timoshenko theory, which is a next level theory, where plane sections remain plane, but normals to cross section do not remain normal. So they change. So this normal won't be normal. It will change a direction. Okay. So there is a certain type of shear strain profile accommodated. Okay. So this together was, this says that the vertical shear strain is 0. That's one assumption. The other in Euler Bernoulli is that rotational inertia is ignored. Rotational inertia is ignored. Okay. So you see all the assumptions that are coming in. So now what's the idea? We have already done or found the Euler Bernoulli beam equation using Hamilton's law. I want to show you how it is done in the book by Werner Sodel. Okay. The reason is that if we see it for an Euler Bernoulli beam theory, then it will be ingrained in our minds forever. We will anyway do it in the way the book does for the entire general shell. Okay. But then there are so many terms that the picture is going to be full picture is going to be confusing. So I want to show you what is the basic method in which the system equations are derived. Okay. So this is the second way. We are again going to use Hamilton's principle. We are again going to use Hamilton's principle, but in the way that Sodel does it in the book. Okay. So here I am going to for now ignore external loads. Okay. It's unimportant at this point, exterior loads. Okay. So what we now begin with is the potential energy is given by U, which is volume integral 1/2 sigma xx epsilon xx plus sigma xz epsilon xz dV. Okay. So at this stage we don't enforce the fact that xz is 0. Okay. We don't do it at this stage. And then delta of U is given by V sigma xx delta epsilon xx plus sigma xz delta epsilon xz dV. How this equation comes from here, I will prove it later for the general case. Right now you accept it. Okay. Then if my total axial displacement is this mid-plane displacement plus z beta, then my epsilon xx is given by del u by del x plus z del beta by del x. Okay. And epsilon xz is given by del by del z u plus z beta plus del w by del x, okay, which is equal to beta plus del w by del x. Okay. Now if we substitute the variations of this and this into delta u, what do we get? We get the delta u given by the volume integral of sigma xx into del x of delta u plus z times del x of delta beta, okay, plus sigma 1 3, sigma xz delta beta plus del x of delta w dv. Okay. Now if we separately write the integrals, delta u is given by 0 to L integral minus h by 2 to h by 2 integral 0 to b sigma 1 sigma xx del by del x delta u, okay, plus z delta beta del x delta beta plus sigma xz delta beta plus del x delta w dy dz dx. Okay. So now there is no dependence on y, okay, so just a b falls out. Okay. So what we have is and if we do the h integral, because this depends only on x, this depends only on x, this depends only on x, and this depends only on x. Okay. So wherever the z dependence is, there is z dependence here, there is a z dependence here. Okay. So if we do that, what we will get is integral 0 to L. Okay. Now sigma xx, okay, so sigma xx, let's say sigma xx is like this. Okay. And integrated over the thickness, we will give it a name nxx. Okay. It is not a full force because sigma xx into the thickness dimension is force per unit length. Okay. So this is called a force resultant. So this sigma xx, after going through the thickness integral, will become nxx del x delta u. Similarly, sigma xx, this sigma xx, whatever profile, if you multiply by z, okay, if you multiply by z, suppose you have some profile sigma z, sigma x, and this is my thickness, my z axis. If I multiply by the sigma by the corresponding z, then I get a moment. Okay, so I get a moment, but that is not a full moment because it is a moment per unit length, just as this was a force per unit length. And so what we get here is plus mxx del by del x delta beta. Okay, this sigma xx into dy and dz makes it a force. Okay, dy and dz makes it a force, and a further z makes it a full moment. Okay, but what we are going to do is separate out the dy integral, which is just a constant, and so we get a moment per unit length. Okay, it will be clear in just a moment. Similarly, the sigma xz integrated gives me a qxz delta beta plus del x delta w. Okay, and the b comes outside, b dx. So mmx into b is a full moment, qxz into b is a full force. Okay, so this is a force resultant, this is a moment resultant, this is a force resultant. Okay, so now what do we do? What we do here is we will transfer these derivatives. Wherever there is a derivative, the variation term will transfer the derivative. Okay, so now my delta u becomes the first we will call it term 1, term 2, term 3. Okay, so we will do term 1. Term 1. Okay, so we have integral 0 to L nxx del x delta u b dx. Okay, so this will be, I will use a product rule, so I get nxx into b into delta u 0 through L, okay, minus an integral which is 0 to L del nxx by del x delta u b dx. Okay, and then I get second term, term 2. Term 2 is integral 0 to L mxx del x delta beta b dx. Okay, so that is equal to mxx delta beta into b 0 to L minus integral 0 to L del mxx by del x delta beta b dx. Okay, and term 3. Term 3 is integral 0 to L, okay, qxz delta beta plus qxz del x delta w into b dx. Okay, so this will be written as, there is no problem here, delta beta appears as delta beta, so we have integral 0 to L qxz delta beta b dx. Then there is a derivative on delta w here, so I get plus qxz into b delta w 0 through L minus an integral 0 to L del qxz by del x delta w